Welcome, everyone. I'm excited to kick off our presentation today on ray optics and optical instruments. This is the first slide, so let me briefly introduce what we'll be exploring. We'll cover the fundamentals of ray optics, how light behaves, and also delve into various optical instruments that help us see and measure things more clearly. So, let's get started and discover the fascinating world of optics together. Let's take a closer look at slide 2, which covers some fundamental concepts in optics. First, we see the phenomenon of light itself, how it behaves and the various effects it produces. Moving forward, we encounter the phenomena of light, which include reflection, refraction, dispersion, and scattering. These are the basic principles that govern how we see and interpret the world around us. Next, we explore the principal focus, a key point in optical devices like lenses and mirrors, where parallel rays converge or appear to diverge. Understanding this helps us grasp how images are formed. Speaking of lenses, the laws of refraction explain how light bends when passing from one medium to another, which is essential for designing optical instruments. We also need to consider spherical aberration, a common distortion caused by spherical lenses or mirrors that can blur images. Minimizing this aberration is crucial for clearer, sharper images. This leads us to applications of spherical mirrors, which are used in telescopes and headlights to direct light efficiently. The refractive index is another important concept. It's a measure of how much light bends in a material, affecting how we see through various media. Total internal reflection is a fascinating phenomenon where light is completely reflected inside a medium, and understanding the conditions for this to occur helps us develop technologies like optical fibers. Speaking of optical fibers, they rely on total internal reflection to transmit light signals over long distances with minimal loss, which is vital for modern communications. These fibers are a prime example of how we apply optical principles in everyday life. Finally, the principal focus and the applications of refraction are central to many devices and phenomena, from simple magnifying glasses to complex telescopes. All these concepts are interconnected, illustrating how the behavior of light shapes much of the technology and natural phenomena we observe. Let's take a closer look at the fascinating phenomena of light, starting with color vision, which is how our eyes perceive different wavelengths of light, giving us the vibrant world around us. Moving on, polarization is a property that describes how light waves oscillate in specific directions, and this has practical applications in sunglasses and photography. The photoelectric effect is another key concept. It's about how light can eject electrons from a material, which was crucial in understanding quantum physics. Next, diffraction and interference involve how light waves bend around obstacles and interact with each other, creating patterns that reveal the wave nature of light. Reflection and scattering are about how light bounces off surfaces or spreads out when hitting particles, shaping everything from mirrors to the blue sky. Refraction describes how light bends when passing through different mediums, like from air into water, which explains phenomena like a straw appearing bent in a glass. Finally, rectilinear propagation of light means that, in a straight line, light travels in a straight path unless acted upon by these phenomena. Altogether, these phenomena highlight the diverse and intriguing behaviors of light, helping us understand its fundamental nature and its role in our visual experience. Let's talk about spherical aberration. This occurs when a spherical mirror with a large aperture can't focus the marginal rays and the central rays at the same point. Essentially, the mirror's shape causes rays hitting near the edge to focus at a different point than those hitting near the center. This leads to a blurred or distorted focus, which is a key limitation in optical systems using spherical mirrors. Understanding spherical aberration helps us appreciate why more precise mirror shapes, like parabolic mirrors, are used in high-precision applications. It ties into our broader discussion on how mirror shape influences image quality and system performance. Now, let's look at how we can minimize spherical aberration. One effective method is by using paraboloidal mirrors. These mirrors are shaped in such a way that they focus light more precisely, reducing the blurring caused by spherical aberration. Another key point is the use of a stop for marginal rays. By placing a stop that allows only the central rays to pass through, we effectively cut off the rays that would otherwise contribute to distortion. Both of these techniques are crucial because they help us achieve sharper, more accurate focusing in optical systems. They tie into our overall goal of improving image quality by controlling aberrations, which is fundamental in designing high-performance optical devices. Shaving mirrors are typically made slightly concave, which allows us to see an erect and enlarged image of our face. This makes it easier to shave accurately and comfortably. Concave mirrors with large apertures are also used in reflecting-type astronomical telescopes. Their ability to gather and focus light makes them ideal for observing distant celestial objects. Additionally, concave mirrors are common as reflectors in table lamps, helping to direct light precisely where it's needed. These applications highlight the versatility of spherical mirrors and how their unique properties are harnessed in everyday life and scientific tools alike. Now take a look at this image. Notice how it's smaller in size, which actually helps us see a much wider area. This is a key feature of convex mirrors. They give us a broader field of view, making it easier to see more surroundings at once. Moving on to the next point, a convex mirror always produces an erect image. That means the image appears right side up, which is very important for safety and convenience. You'll often see these mirrors used in automobiles as rear view mirrors. Why? Well, there are two main reasons. First, because they provide a wider field of view, helping drivers see more of what's behind them. And second, because the images they produce are upright, making it easier to interpret what you're seeing without confusion. So, in summary, convex mirrors are a smart choice for situations where safety and visibility are crucial, like in cars, thanks to their ability to give us a broad view and upright images. Now, let's talk about how light behaves when it encounters a boundary between two different media. When an obliquely incident ray of light hits this interface, its direction of propagation actually changes as it enters the second medium. This change in direction is what we call refraction of light. Essentially, refraction occurs because light slows down or speeds up depending on the optical properties of the media involved. This phenomenon is key to understanding how lenses work, how we see clearly through glasses, and even how rainbows form. So, in summary, whenever light passes from one medium to another at an angle, expect its path to bend. That's the essence of refraction, a fundamental concept in optics that connects to many everyday applications. Now let's look at Snell's law. This tells us that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. Essentially, this means that when light passes from one medium to another, the change in direction is predictable and governed by this constant ratio. It's also important to remember that the incident ray, the refracted ray, and the normal to the point where the light hits all lie in the same plane. This plane is crucial because it simplifies how we analyze the behavior of light at the boundary. Together, these points form the core of the laws of refraction, which help us understand how light bends and behaves when moving through different materials. This understanding is fundamental in optics, from lenses to fiber optics, and ties right into the overall theme of how light interacts with various media. Let's take a closer look at the formula N equals C over V here. N represents the refractive index of a medium. It's essentially a measure of how much light slows down when it passes through that medium. The key point is that the refractive index is defined as the ratio of the velocity of light in a vacuum, which we denote as C, to the velocity of light in the medium, which we call V. This ratio tells us how much the light's speed is reduced inside the medium compared to a vacuum. The higher the refractive index, the more the light slows down. This concept is fundamental because it helps us understand how light bends or refracts when it moves from one medium to another. Connecting this to the overall theme, understanding the refractive index allows us to predict and explain phenomena like bending of light in lenses, the focusing of optical devices, and even the behavior of light in different materials. So, grasping this ratio is crucial for a deeper understanding of optics and the behavior of light in various environments. As we look up at the night sky, we notice that stars appear to twinkle. This interesting phenomenon happens because, as the light from a star travels through Earth's atmosphere, it passes through layers of air with different densities. Now, as we go higher in the atmosphere, the air becomes less dense or rarer. But closer to the Earth's surface, the air is denser. So, when the star's light moves from these less dense, rarer layers to denser layers, it bends or refracts towards the normal, which is an imaginary line perpendicular to the surface. This bending causes the star to appear at a slightly different position in the sky than where it actually is. However, the key point here is that the density of the atmosphere isn't constant. It keeps changing due to temperature variations, air currents, and other factors. Because of this continuous change, the apparent position of the star keeps shifting slightly. And this constant shifting creates the twinkling effect we observe. So, in essence, the twinkling of stars is all about the dynamic nature of our atmosphere and the way light bends as it travels through these varying layers. As we go up, the density of air in the atmosphere continuously decreases. So, the light coming from the sun travels from a rarer medium to a denser medium. Because of this, it bends towards the normal line. This bending causes us to see the sun at an apparent position that's actually raised above the horizon. That's why we experience early sunrise and delayed sunset. It's all about how light bends when passing through layers of different densities in the atmosphere, affecting our perception of the sun's position in the sky. When light travels from a denser medium to a rarer medium, something interesting happens if the angle of incidence is large enough. If this angle exceeds a certain critical value, instead of passing through the boundary, the light gets completely reflected back into the original medium. This is what we call total internal reflection. It's a fascinating phenomenon because it allows light to stay trapped within a medium, which has practical applications like fiber optics and optical devices. Understanding this concept helps us grasp how light behaves at boundaries and how we can harness these effects in technology. When considering the conditions for total internal reflection, the angle of incidence plays a crucial role. It must be greater than the critical angle, which means the light hits the boundary at a steeper angle than this specific threshold. Additionally, for total internal reflection to occur, the light must be traveling from a denser medium to a rarer medium. This is key because it's only under these circumstances that the light is entirely reflected back into the denser medium, rather than refracting out into the less dense medium. These conditions together ensure that the light doesn't pass through the boundary, but instead is completely reflected, which is fundamental in applications like fiber optics. Remember, the overall theme here is understanding how light behaves at boundaries, and these specific conditions allow us to harness total internal reflection effectively. On hot sunny days, the layer of air in contact with the sand in a desert gets heated up quickly. The upper layers of air, however, tend to stay cooler and become denser. When light from a distant object, like a tree, travels downward, it moves from a denser medium, meaning the cooler, heavier air, into a rarer medium, which is the hotter, less dense air closer to the ground. Because of this change in density, the light ray undergoes a phenomenon called total internal reflection. For an observer, this means the image of the distant object appears to be inverted. It creates the illusion that the tree is standing near a pool of water, even though there's no water there at all. This optical illusion is what we call a mirage. Understanding this phenomenon is important because it highlights how variations in air temperature and density can affect the path of light, leading to fascinating visual effects in nature. Let's talk about the brilliance of a diamond. As you can see, the refractive index of diamond is very high, specifically 2.42. This means that light slows down significantly when it enters the diamond, causing a lot of bending or refraction. Now, the critical angle for diamond is quite low, around 24.4 degrees. This low critical angle plays a crucial role in how light behaves inside the stone. The faces of a diamond are carefully cut to maximize this effect. When a ray of light enters the diamond, it doesn't just pass straight through. Instead, it undergoes multiple total internal reflections inside the stone. These reflections trap the light inside, bouncing around until it finally exits through a few specific faces. And it's this precise cutting and internal reflection that give diamonds their characteristic glitter and sparkle. The way the light is trapped and then released through these faces is what makes a diamond so dazzling and visually captivating. It's a perfect blend of optical properties and craftsmanship that creates that mesmerizing brilliance we associate with diamonds. Optical fibers are quite fascinating because they serve multiple important functions. One key use is in carrying electrical signals that are converted into light. This process allows for efficient data transmission over long distances with minimal loss. It's a crucial technology in telecommunications and internet infrastructure. Another interesting application is in medical examinations. Optical fibers act as a light pipe, which means they help us see inside the body without invasive surgery. They are used in devices like endoscopes to examine internal organs, providing clear visuals and aiding in diagnosis and treatment. Overall, optical fibers are a perfect example of how light can be harnessed for both communication and healthcare, connecting different fields and improving our lives in many ways. Today, we're going to explore an interesting phenomenon called dispersion of light. Essentially, dispersion occurs when a composite light, like white light, splits into its individual colors. Now, when white light passes through a prism, it doesn't just bend or refract randomly. Instead, it separates into 7 distinct colors. These colors are often remembered by the acronym VIBGYOR: violet, indigo, blue, green, yellow, orange, and red. This process beautifully demonstrates how white light is made up of multiple colors, each with different properties. Understanding dispersion helps us grasp how prisms work and also explains why we see rainbows in the sky. It's a fundamental concept that connects to the broader theme of how light behaves and interacts with different objects. So, next time you see a rainbow, remember, it's a perfect example of dispersion in action. A rainbow is truly a fascinating natural phenomenon, and it forms through a combination of 3 key effects: dispersion, refraction, and total internal reflection, that all occur as sunlight interacts with raindrops. When sunlight enters a raindrop, it slows down and bends, or refracts, because of the change in medium. This bending causes the different colors within sunlight to spread out, a process known as dispersion. As the light hits the back of the raindrop, it reflects internally, bouncing back inside the drop. Then, as it exits the raindrop, it bends again. The combined result of these processes, dispersion, refraction, and internal reflection, creates the beautiful, colorful arc we see as a rainbow. It's amazing how these physical effects work together to produce such a stunning and familiar natural display, connecting the principles of optics to everyday wonder. So, what we're looking at here is the concept of scattering. Essentially, scattering occurs when light encounters particles in the atmosphere, like dust or air molecules. These particles are irregular in shape and size, which means they don't reflect light in a straightforward, predictable way. Instead, they cause the light to scatter in different directions. This scattering is partial and irregular, which is why the light doesn't just bounce straight back or pass through unaffected. It's a key process because it influences how we perceive the sky's color, how sunlight diffuses during the day, and even phenomena like the redness of a sunset. Understanding scattering helps us see how light interacts with the atmosphere in a complex, dynamic way. This idea ties back to the overall theme of how light behaves in our environment and how this behavior affects what we see around us every day. When sunlight enters the Earth's atmosphere, it doesn't just pass straight through. It actually interacts with dust particles and air molecules along the way. This process is called scattering. Now, what's interesting is that the scattering affects different wavelengths of light differently. The shorter wavelengths, like blue and violet, are scattered much more than the longer wavelengths like red or yellow. Since our eyes are more sensitive to blue light than violet, the scattered blue light dominates what we see. That's why, when we look up at the sky during the day, it appears blue to us. This phenomenon is a perfect example of how the atmosphere influences the way we perceive light and color, tying into the broader theme of how natural processes shape our visual world. When we observe the sun during sunrise and sunset, something interesting happens. The light from the sun has to travel through a much thicker layer of Earth's atmosphere. Because of this longer path, the shorter wavelengths of light, like violet and blue, are scattered away more effectively. That leaves the longer wavelengths, especially the reddish and orangish hues, to reach our eyes. This scattering process is called Rayleigh scattering, and it's the reason why the sun appears red during these times. It's a beautiful example of how the Earth's atmosphere influences the way we perceive the sun's color, connecting to our overall understanding of light and visibility. The reason the sea appears blue has to do with how sunlight interacts with the water molecules and dust particles in the atmosphere. When sunlight enters the water, it doesn't just pass straight through. Instead, it gets scattered in different directions. According to Rayleigh's scattering law, the shorter wavelengths of light, like blue, are scattered more than the longer wavelengths, such as red or yellow. This means that the blue part of sunlight is scattered more widely throughout the water, giving the sea its characteristic blue color. So, essentially, the scattering of sunlight by water molecules causes the sea to look blue to our eyes. This concept ties back to the broader theme of how light and particles interact in our environment to create the colors we observe. Let's take a closer look at the eye. The eye is often considered the window to the soul, but in our context, it also represents perception and awareness. It plays a crucial role in how we observe and interpret the world around us. The way we see things influences our understanding and decisions, which ties directly into the broader themes we've been discussing about perception and insight. Remember, just as the eye gathers light and transforms it into vision, our minds process information to create understanding. So, the eye isn't just a physical organ, it's a powerful symbol of perception, focus, and clarity that underpins our entire exploration today. Now, let's take a moment to talk about the telescope. The telescope is truly a remarkable tool that has revolutionized our understanding of the universe. It allows us to see distant stars, planets, and galaxies that are otherwise impossible to observe with the naked eye. By collecting and magnifying light from these celestial objects, telescopes enable astronomers to analyze their composition, motion, and even their history. What's fascinating is how the development of telescopes has expanded our cosmic horizon, pushing the boundaries of what we know and opening new questions for exploration. From early refracting telescopes to modern space-based observatories, each advancement has brought us closer to understanding the universe's vastness and complexity. So, in the context of our overall theme, discovery and innovation, the telescope stands as a symbol of human curiosity and our relentless pursuit of knowledge. It reminds us that with the right tools and a curious mind, we can unlock the secrets of the cosmos and, in turn, deepen our understanding of ourselves.